Welcome back to RobotGeek 101. Today we're going to take a look at analog sensors. So in the past we've looked at digital sensors like this push button. I can get a high or low signal by pressing the button or letting it go, but that's it. I can only get high or low. An analog sensor, on the other hand, can have a wide variety of values from 0 to 5 volts. So this knob, for example, as I turn this, can actually generate between 0 and 5 volts. So when it's in the middle, it can generate 2.5 volts. I can turn it to 3 volts, 4 volts, all the way up to 5 volts. This same concept, this potentiometer that's in this knob, can actually be turned on its side so that now I've got a joystick with two axes. So each axis that I turn on can send different signals to the Geekduino. And I've got the slider over here that uses similar technology to generate different voltages as I slide. I've also got two of my favorite analog sensors here. One is a light sensor. This little photocell changes resistance as light hits it, and this little chip amplifies that signal so that the board will get 0 to 5 volts depending on how much light this cell is getting. I also have a force sensing resistor that changes resistance as I push down on the sensor. So by changing that resistance, I can change my 0 to 5 volt signal, and my Geekduino can know whenever I'm pressing down on this sensor. For this video, we are going to focus on the rotation knob. It's small, easy to use, and has a nice linear output, so it's easy to understand. And right here, I've actually taken one of these apart. So I've taken apart this metal housing, taken off the knob, so you can see what the internals look like. I've got some metal down here, and that's going to act as the wiper. We'll talk a little bit about the wiper in a minute. And then you've got the heart of the potentiometer here. So through our PCB, we're doing a little bit of pin mapping. This G will actually go over to this pin here, S to the middle pin, and V voltage over to this pin. Basic idea is that the signal pin in the middle here is conductive with this inner ring, and this black part is a resistor that's conductive at any point. So if I measure at any individual point, I will get a different voltage. If I measure all the way over here, I'll get 5 volts since it's attached to V. If I measure over here, I'll get 0 volts. If I measure right in the middle, I'll get 2.5 volts. So if you take a quick look at our diagram, you've got 0 volts here, like I mentioned, 5 volts here. And imagine that knob, the metal piece, has a wiper that connects from this outer ring to this inner ring. So as I turn the wiper, I can get different voltages out of my signal pin. So I get 0 volts, 1 volt, 2 volt, 2.5, 3, 4, all the way up to 5 volts in all sorts of different increments. If you want to see this in practice, you can get out a multimeter. A multimeter can measure different electrical characteristics like voltage. That's what we'll be measuring here. And I've got this board hooked up to a 3-pin cable over to my Geekduino, supplying it with 5 volts. If I go and put one lead on ground and one lead on 5 volts, I should get pretty close to 5 volts, 4.95. So not exact, but that's what my Geekduino is putting out. Here, if I put on this black, I should still get towards that 4.96. And as I start dragging this, you're going to see that value change. So right around here is 4 volts. Right around here is 3 volts. Right in the middle, I should have 2.5 volts. Over here, I'll have 2 volts. And over here, I'll have 1 volt. So by connecting that wiper from the middle ring to the outer ring, I'm just sending this voltage directly to the Geekduino, and the Geekduino can then measure that voltage and tell its program what that voltage is, thus interpreting the analog sensor. Let's take a look at hooking up our RobotGeek sensor shield to the analog sensor and how the Geekduino interprets it. Now these 3-pin cables can be used to be hooked up to digital inputs and outputs, but only the 8 here marked analog can properly read analog sensors. So as usual, we'll take a 3-pin cable, make sure we've got S, V, and G hooked up. On the other end, we will check S, V, and G, Make sure S is on white, and we're going to hook it into analog IO0. This is different from digital IO0, so make sure you've got your numbers right. For our code, we'll go to File, Sketchbook, RobotGeek Sketches, RG101, Analog Input, Serial Output. This sketch is going to read analog data and then put out that data on the serial monitor. So let's go ahead and upload it. Once we're done uploading, we can click on Serial Monitor. And we should see analog value and voltage. Right now it's focused on voltage. So since I'm plugged all the way to the left on this knob, I should see 0 volts. As I bring this up, my voltage will go up and up and up. If I turn it all the way to the right, I should have 5 volts. Right in the middle, I should have 2.5 volts. Now you're also going to see the analog value change, and that value changes from 1023 down to 0. The analog value is determined by a device called the analog to digital converter, or the ADC. The Arduino has a 10-bit analog converter, and that means that you've got values from 0 to 2 to the 10th power. 2 to the 10th power is 1024, so that's where we get 0. 0 is a single number, all the way to 1023. And you can think of analog value as a fraction. So when I'm in the middle here, and I've got 2.5, you should see 512 for your analog value. 512 divided by 1023 is half 0.5, and 0.5 times 5 volts gives us a voltage of 2.5. If we take a look at this diagram, you can see what I'm talking about. 0 volts, the analog volt value is 0. 5 volts, the analog value is 1023. Then here at 2.5, I've got approximately 512. 2 volts, I've got approximately 409 as my analog value. 1 volt's 204, 3 volts 613, 4 volts 814. These are all approximately because as fractions, you're not going to get exactly 4 volts. You're going to have some leading digits. So let's take a look at the code. We've got our constant integer for our analog pin, just like in our other code. We have an integer holding our analog value. That's the value from 0 to 1023. This time we have a float holding our analog voltage, and a float is a value that has decimal points. So that's why we can have 2.5 or 1.76. If we were to use an integer here instead of analog voltage, instead of a float for analog voltage, we would only have whole numbers like 0, 1, 2, 3, 4, 5. Here we're starting our serial port, and we're printing the serial test print analog sensor message to start communications. Analog pins don't actually need to be explicitly set to pin mode input. There's no problem with setting them to input if you want, but there's no need to either. In our loop, we're using this analog read function, very, very similar to the digital read function where we put in this pin. Keep in mind the analog pin 0 is this analog pin in the upper left corner. The main difference is that this reads from the analog pins and then gives out that value from 0 to 1023. So here we're storing it in analog value. Now to get analog voltage, we're going to have to do a little bit of math. Like I said before, the analog value is essentially a fraction of 1023. So if I bring out my calculator, when I had 512, divide that by 1023, gives me 0.5. So that's this, 0.5. Then I multiply that by 5 volts, which gives me my 2.5. Right here I have my analog value of 361. I'm going to divide that by 1023. 0.352, I'm going to multiply that by 5 volts, and I get 1.76. So that's the math that I'm using to get my analog voltage. Once I have my value, my voltage, it's really easy to use the serial print statements to print them out to the serial monitor. I've got a delay here just to slow down the serial monitor. I don't want it filling up the buffer too fast. So that's the core of reading analog values. Now, you're going to use a lot of different formulas to get different values. For the most part, you're not actually going to use this formula to give it out to voltage because you're going to handle the data differently when you're in the Arduino world. But you normally will use some kind of formula to convert the data into the kind of data you want. So getting it from that 0 to 1023 to the range that you need. Next, we're going to take a look at File, Sketchbook, RobotGeek Sketches, RG101, Analog Input, Analog Blink Control Delay. This code is going to need an LED, as we see here. LED pin is 13. So we're going to grab our LED pin, make sure our white is to S. On the same token, over here on digital pin 13, we'll have white on S. We'll go and upload this code. And what you're going to see is the LED blinking at different rates depending on where the knob is. So as I turn the knob up and up, the LED is going to take longer and longer to blink. So I've got my constant integer pins, my analog value. I also have an LED state held in a boolean since the LED will only be on or off. I have a delay time, which will be the amount of time I determine between LED blinks. I'm setting the pin mode for my LED as an output. Then in my loop, I'm reading the analog pin just as before, but here I'm using a different formula. The default value from the analog sensor, 0 to 1023, would give me from about 0 to 1023 milliseconds, so just about 0 to 1 seconds for a blink. I wanted something longer, so I went times 5. So that gives me from 0 to 5,115, or about 0 to 5 seconds. I added this constant 100 because at the low range, at 0, I actually want it to be a little bit slower. If I blink it too fast, I won't be able to see the blink. So this will now be mapped from 100 milliseconds to about 5,000 milliseconds, or 0.1 second to 5 seconds. The first thing I do is invert the LED state using the exclamation point. So again, high goes to low and low goes to high. That means every time this loop runs, the LED is going to flop its state. I'm going to write that digital pin, LED pin, to that LED state using digital write. And then I'm going to delay for that delay time. Now remember, like we discussed in the original Blink code, this delay time means that this loop is stuck. It's just not going to be doing anything while it's delaying. And you can see that here, that if I'm blinking very slowly, all the way at 5 seconds, if I bring this down really quickly, this blink needs to finish before it's going to catch up and start blinking at the new rate. In another video, we talked about blinking without delay. We can actually use the same technique to make this code much more responsive. So let's go to File, Sketchbook, RobotGeek Sketches, RG101, Analog Input, you guessed it, Analog Blink Control without delay. We're going to upload this code, and we're not going to go too far in depth because the other video does a really good job of explaining how all of this works. But as you can see, at the higher end, I'm still blinking at about 5 seconds per blink. But if I bring it down really quickly, it changes the value immediately, making it much more responsive. The main differences are that I added this variable. This unsigned long gives me a much wider range of values than the integer, but it's still just whole numbers. Down here I'm using the millis function. That's how many milliseconds since the Arduino started. I'm subtracting the last time that the LED toggled, and I'm taking that value and comparing it to delay time. The delay time still being the same from this analog sensor read. If this time difference is more than the delay time, then it's time to flip-flop the LED. So I can do just like I did before, change the state and write the LED. I still need to update this last blink time so that every time it actually runs this if code, it knows to start counting again. But with just these couple of changes, we've made the code a lot more responsive. And again, for this particular example, it might not be that important, but as your code gets more complex, using minimal delays and blocking less is going to help you a whole lot. We will have some videos on advanced analog sensor topics like multiple sensor reads and averaging. But right now, you know everything you need to know to go on to the next lesson, pulse width modulation in RobotGeek 101.